Welcome back to Organic Chemistry 1. We are moving straight into Chapter 7. And in Chapter 7, we're going to talk first about alkyl halides and then two of the very important classes of reactions that they participate in, one being substitution and the other being elimination. So we'll get to that later, but for now, let's go ahead and we're just in this lecture going to talk about section 7.1 and I think 7.2, which should be just, the definition of what alkyl halides are, and then talking about their nomenclature, which you're already familiar with. So that's just going to be mostly a review. So yeah, so as I mentioned already, alkyl halides undergo substitution and elimination reactions. And as far as like what alkyl halides are, well, you can kind of piece it together, right? It's alkyl halide. So this is basically an alkane or something substituted like an alkane, and it's substituted with a halogen. So fluorine, chlorine, bromine, or iodine. And in alkyl halides in particular have to have the halogen substituent on an sp3 hybridized carbon. So just keep in mind, like the only one that's going to undergo substitution or elimination as far as an alkyl halide reaction goes is going to be the sp3 carbon. When we get to the alkenyl or the benzyl, for example, or the phenyl halide, that has a whole other set of reactions that we'll talk about. We're going to talk about this one next semester, and I think this one we'll talk about later this semester. Okay, so we mentioned already these names of these reactions, the substitution and the elimination reactions. The good news is basically the reactions do exactly what the name says. So a substitution reaction, what happens is a nucleophile is going to substitute itself for the halogen. So the halogen group leaves as a halide. So imagine this is chlorine. That means you're going to leave as a chloride. And then what was the carbon X bond is now going to be a bond to a new nucleophile. So it's like your carbon N bond here. So this is a very generic version of that. And there's two different routes, two different mechanisms that this goes under. It can be SN1 or SN2. So we'll talk about both of those later on in this chapter. That's why we haven't drawn in a mechanism here. But you can imagine basically what it is. It's a combination of a nucleophilic attack and a loss of a leaving group. So let's go ahead and draw in. I'm going to draw in the SN2 mechanism. We'll talk about what that means a little bit later. But what happens in SN2, you have a nucleophilic attack on the electrophilic carbon here. And then at the same time, as that nucleophilic attack occurs, you have the loss of a leaving group in the form of this halogen. So hopefully you can see, like, we have the combination of those two arrows means that we're going to end up with a new bond between carbon and the nucleophile, and then the leaving group, that's the halide, that's left as just a halide. So that's the substitution reaction. Elimination, on the other hand, elimination involves a base, and elimination is exactly what it sounds like. It's going to be a way that you eliminate the halide from the compound. And what actually happens is a proton on a neighboring carbon. So we'll talk about this a little bit, but the carbon that's bonded to the halogen, that's the alpha carbon. Any carbon that's bonded to the alpha carbon then becomes a beta carbon. So any of these beta hydrogens here, any hydrogens that are bonded to the beta carbon, they can be deprotonated. And when they're deprotonated, again, I'm just going to go ahead and show you the E2 mechanism here. We have a proton transfer from this beta carbon to the base, and that forms our conjugate acid. At the same time, we form a new pi bond, and we kick off the halogen as a halide. So we have a loss of a leaving group, and we form a new pi bond here from this carbon H bond electrons. This, again, in particular, is the E2 mechanism. There's also an E1 mechanism that we'll talk about later on. But that just kind of gives you an idea of the patterns of electron movement that we're going to see. So yeah, so you can have a substitution when it's reacted with a nucleophile, and then an elimination when it's reacted with a base. Now, there's an issue that pops up here, and this is something that we'll talk about in great detail. And trust me, this is kind of the key later on in this chapter, is the balance between things that are nucleophiles and things that are bases. So a lot of times strong bases are also strong nucleophiles, and vice versa. Like if it's a strong nucleophile, that means that this lone pair really wants to be filled in. So it's going to grab a proton or whatever it can. So we'll talk about that a lot later this chapter. Okay, so yeah, so I guess I just basically said this, but if you have a reagent, so for example, sodium hydroxide, hydroxide is a strong base and it's also a really good nucleophile. It's got a negative formal charge on the oxygen. So it's a really strong nucleophile. And what that means is basically you can expect to get both the elimination product and the substitution product. So just keep in mind that these are going to be competing pathways, and we will need to use our chemical intuition and our chemical knowledge to be able to figure out which one's going to be the major product in the future. And then also, when we design our own experiments, like we're going to want to either have the substitution or the elimination product. And I'll talk about some tools that you can use to help you bias it one way or the other. Okay. So looking at substitution and elimination reactions, why do they occur? Well, there's a few things, which is that whenever carbon is bonded to a halogen, the halogen is going to be electron withdrawing. It's got more electronegativity, so it's going to pull the covalent electrons to itself. And that means you have a partial negative charge on the halogen, and that leaves you with a partial positive charge on the carbon. In other words, you're going to have an electrophilic carbon. So an electrophilic carbon is going to be subject to a nucleophilic attack. Also, halogens are really good leaving groups. So we've talked about these kind of vaguely in the past, but now we're going to look at specifically what makes a good leaving group. But for now, all we need to know is like it forms a stable leaving group, so that makes it a very good leaving group. And so here is kind of the ranking of our leaving groups here. So the best leaving groups are basically just like the conjugate bases of strong acids. Like hydriodic acid has a pKa of -11. Its conjugate base, iodide, that's like a very strong, that's a very strong acid, and that means that the conjugate base is very stable. So that means that iodide is like our best leaving group. Then there's also bromide and chloride. Water can also be a good leaving group. And then we also have like sulfonates here, like what we see here. So we'll talk about this. This is para-toluene sulfonate. It makes a really good leaving group. There's a reason that we bring it up here. It's going to be very important to us later on. So, but we'll abbreviate it. So we're just going to point out this structure here for now. And then bad leaving groups are basically conjugate bases of weak acids. So like HF is a weak acid. So that means that fluoride is going to be a very weak leaving group. Same thing with hydroxide, and then any of the conjugate bases of alcohols or amines especially would be a really bad leaving group. So this is just how we're going to classify it as we move forward. Okay, so as far as like naming alkyl halides, there's nothing really different. Remember that the substituents are just going to be F is fluoro. Always remember fluorine is FLUORO, like so the fluoro is FLUORO. I know that's a hard one to remember, but you will get it wrong on the test if you flip the O and the U, so keep that in mind. Chlorine, chloro, bromine, bromo, iodine, iodo. And yeah, that's just you already know that, but we're just going to review that here. So that's the key. Yeah, so go ahead. We just want to like go ahead and remember that we want to always number our parent chain. So you identify the parent chain, the longest possible carbon chain, and then you're going to number it so that you have the lowest numbering scheme possible, starting from the first substituent. So like 1, 2, 3, it doesn't really matter which way you number it, but this one, obviously you want to start left to right, 1, 2, 3, 4, 5, so that the bromo and the methyl are on carbon 2. And then finally down here, you have a choice between a methyl group on carbon 2 or the other way, bromo would be on carbon 3. So you go with the lower number, which is the 2. Also no surprise here, because we're dealing with halogens, that means we're going to have a lot of stereocenters to consider chiral centers. So don't forget the R and the S configuration of any chiral centers. Now, there's also a couple of these that you just want to be able to recognize the common names for. So in particular, In lab, like if you guys were going into lab, one of the most common solvents that we use is dichloromethane, which just makes sense. It's like you have two chlorines on one carbon and you don't need to number it, right? So it'd be, what would it be? 1,1 dichloromethane, like, but there's only one carbon. Where else could they be substituted? So this is the systematic name dichloromethane. But chemists a long time ago used to use the naming scheme methylene chloride. And this is still on a lot of jars of solvent that you see around the lab. So because it's so commonly used, people kind of hold on to the older name there as well. I'm not going to quiz you on the common names necessarily, but there's just a couple that you should be able to recognize. In particular, methylene chloride, again, which is dichloromethane. Trichloromethane, you would never hear that word, that's chloroform. So if you draw 3 chlorines sticking off of this, that's chloroform. And then carbon tetrachloride is like not used very commonly anymore because it's pretty carcinogenic, but used to be like a fire extinguisher that they would use. Okay, so here, we can do some more practice here, but I know you guys, we just finished up like a nomenclature chapter, so well, okay, give this a try. Go ahead, pause the video, and when we come back, I'll have the names written up for you. So go ahead, give it a pause. Okay, so for my names over here, I got S2-bromo, 2-iodo, 3-methylbutane. And then over here, it was 2R, 3R, 2,3-dichloro, 4, and then you have a choice. It's complex substituent. It could either be isopropyl or 1-methylethyl, and then 5-methylhexane. So that's what I got here. Let me know if I got those wrong in the comments down below, and a little card will pop up here and I'll say, hey, I got it wrong, but I think I got it right. Okay, so let's go ahead and move on. Oh, let me clear those. There we go. Great. Now, I already mentioned this earlier, but let's go ahead and make sure that we kind of cement it here. When we have an alkyl halide, we like to label the carbons where the halogen group is attached. So in particular here, so this is 2-bromobutane. The carbon that is attached to the bromine is labeled as the alpha carbon. Then carbons that are attached to the alpha carbon become the beta carbon. And then beyond that, it's called gamma, and it would move on, but rarely are we going to go beyond beta. Like that's the most important thing to be able to recognize. So you just need to recognize, okay, so the alpha carbon, that's where the halogen is attached. The beta is going to be attached to the alpha carbons. And that's what you need to be able to recognize. Now the question, why do substitutions occur at the alpha carbon? Well, the alpha carbon is directly attached to the electronegative halogen. So that means that it's going to have the partial positive charge. And that effect is going to diminish as you go further away from that halogen. So we need to be able to recognize that. We also figure out from alpha carbon, we figure out what kind of alkyl halide we have. If the alpha carbon is attached to one other carbon, so there's one beta carbon present, that's a primary alkyl halide. If it's attached to 2 carbons, that's a secondary alkyl halide. And if the alpha carbon is attached to 3 carbons, that's a tertiary alkyl halide. So we just kind of want to be able to recognize when we say primary, secondary, tertiary, we're always talking about the alpha carbon. And that's how we're going to kind of recognize this designation for alkyl halides. So yeah, so for example here, well, these are some bad examples here, but if we look here, like this chlorine is attached to this carbon is attached to 2 other carbons. So this is a secondary alkyl halide. Now down here, it's a little tricky, but this carbon is only attached to 1 other carbon, so it would be considered a primary alkyl halide. So just keep that in mind. And then, so for example here, on the right, this structure is a little easier to kind of see here. This would be the alpha carbon. And if we're just focusing on this one, then that means the beta carbons would be here and here. Although then we've recognized these are also bonded to chlorine. So these could also behave as alpha carbons if they were going to. Over here, we only have the 1 alpha carbon bonded to the beta carbon down here. Yeah, and these alkyl halides show up a lot. Like we use them a lot in lab. There's a lot of important solvents that use them, like dichloromethane that we already looked at. organohalides tend to be very reactive. In particular, they can react with DNA and proteins, and what they do is they shut them down. So a lot of them can be used as like insecticides and also like drugs. So like a lot of anti-cancer drugs involve the use of these organohalide groups. And then there's a bunch of other ones. So like Splenda, for example, is like a sugar molecule that's been chlorinated. And then because it's been chlorinated, you can't process it the same way as you do a normal sugar molecule. So while on the tongue it tastes sweet, it actually can't be processed by your body. So you don't gain any calories from it. And yeah, there's also dyes, for example. So there's a lot of these molecules that we're going to be seeing later on. But for now, that does our introduction. So we've covered through section 7.2. And in the next section, I think we're going to talk about substitution reactions. So see you soon.